Hello, Professor Simmons here. Let's talk about constant acceleration and free fall. So previously we talked about some different quantities, displacement, velocity, acceleration. Um, Now we're going to sort of build up a toolbox of a few uh, equations that can be super useful when solving kinematics problems. Um, and these expressions are all assuming that you have constant acceleration. So let me just try and really emphasize that. When you have constant acceleration, um, we can come up with these expressions. So the first thing that we're going to come up with is if we refer back to our definition of average acceleration, we know that it's the change in velocity over the change in time. And the thing is if we have a constant acceleration, that means that the average is going to be the same as the actual acceleration because it's not changing, it's constant. And we can expand this a little bit. These deltas, recall, this means the change in something. So this would be the velocity minus the initial velocity over the time minus the initial time. A lot of times we don't really have an initial time because we can imagine just starting our stopwatch when we are observing the motion. So there's not a t naught per se, it's 0. But notice what this gives us is we have this expression where acceleration, so recall I just told you that the acceleration will equal the average acceleration because it's constant. And so what that means is that acceleration is v minus v naught over t. We can then solve this for velocity, and we get an expression v equals at plus v naught. Okay. And I think it's useful to think about this as velocity as a function of time is at plus v naught. Okay. Now this is one of these expressions that we'll have in our toolbox, and this is, I should mention, this is section 2.5 in your textbook. You can also get this from calculus. So we have kind of a spectrum in terms of how much calculus folks have had. But recall that the acceleration, the actual definition is that the acceleration is the derivative of velocity. So what you can do is you can integrate the acceleration to find the velocity. So if you integrate the acceleration, assuming it's a constant, it's just a number, right? What are you going to get? Well, a constant, the integral of a constant, you would pick up a factor of t plus a constant. And in this case, usually I think in calculus you denote the constant as just a big, a big C or something like that to indicate constant. But in this case, this has actual meaning. So what is the constant? The constant is V naught. So in other words, you can get the velocity from the acceleration by integrating it. And when it's constant, it's basically the simplest integral. You just pick up a factor of t. Okay, so what other expressions do we have? Well, another thing that we can make use of is the fact that if the acceleration is constant, that means that, so think of this as a plot, v as a function of time. This means that this would look like a line. Okay. So with a slope of a, and this is a connection that we'll emphasize in lab, in actually multiple labs, but the free fall lab first. So notice that since this is a line, if you were to start at some initial velocity, and say you end up here at some v2, notice that the average, when the acceleration is constant, will just be the average of the two. So this is another expression that we'll use occasionally when solving problems, this relationship. Notice that this isn't the case if the acceleration isn't constant. If the shape of this was different, suppose it was like that, the average of v0 and v2 would not be v0 plus v2 over 2. This only works when the acceleration is constant. Okay, so that's another expression that you can have filed away. Another one that's really useful is this one. So this is the position as a function of time. Again, when the acceleration is constant. I'm just using x. Usually that would be when we're talking about something that's moving, horizontally as opposed to vertically. But in any case, this expression is very useful. It gives us a expression for x as a function of time, and it depends on v, the initial velocity, and it depends on the acceleration, when the acceleration is constant. Now notice we can get this from our velocity expression as well, because recall, remember velocity is the derivative of position. So if we wanted to get x, we can integrate velocity with respect to time. We have an expression for velocity already. Okay. Actually, and I should mention as an aside, if you haven't seen integration before, don't sweat it. I'm not going to ask you to do a bunch of integration at this point. This is more just to kind of make some connections to math. So I know some of you will have seen this and some of you won't have at this point, and that's totally fine. It's just it's kind of an interesting connection because it's a very concise way to derive these expressions. So notice now if you have AT, you integrate that, what would you have? You'd pick up a factor of 1/2 t raise this to power 2, our v naught piece would pick up a factor of t plus a constant again. And notice that in this case, what's the constant? Well, this would be the initial position. So notice, just with a simple integration, you can get this expression immediately. Your textbook derives this algebraically. So if you want to see their algebraic argument, if you look in section 2.5, I'll just put a note here. They'll show you how to get that without using calculus. But there's one more expression that we want to have in our toolbox that you'll find that you use all the time. And this one is really useful because it does not have time in it. And this expression is the following. So again, just to emphasize, if you have a situation where you have constant acceleration, and actually I'll just call this v here. You can relate the final velocity to the initial velocity, the acceleration, and the distance traveled through this expression. V final squared is going to equal V initial squared plus 2 times the acceleration times the distance. So these 4 expressions are very useful. You're going to use them to solve lots of problems, and they're in your homework. So let me show you an example. So the example that I want you to consider is runway design. So here's the situation that I want you to consider. So an airplane, suppose you have some airplane that needs a minimum speed. (27.8 meters per second to lift off. And has an acceleration of 2 meters per second squared. Will a 150 meter runway be sufficient? Will it be long enough? So to try and model this, a really good practice is to draw yourself a little cartoon. So far, we don't have tons of quantitative things floating around, so our cartoon is going to be really simple, but we have this runway that's 150 meters long. Got a little, however we can try and draw an airplane on here. It can accelerate at 2 meters per second squared. Sometimes there's information that's given that's not explicitly given. So another piece of information that we know is that this airplane is going to start from rest. So that's a way of saying that V naught will be 0. And we know that we need V to be 27.8 meters per second in order for this thing to, be able to take off. So this is a good example in terms of being able to apply the last expression that we mentioned. Notice none of the information that we've been given involves time. But we do have a distance and we do have an acceleration. So there's different ways that we can approach this. Physics, I would recommend to you that there's not one right way to do a problem. A lot of times there's lots of ways to do a problem. So we can do it in a couple different ways here. And I would encourage you to do kind of the same thing. Approach problems from different ways. And it's a great way to practice. So let's see what happens if we just put in the length of the runway and the acceleration and find v final. So we can solve this for v final. Notice this will go to 0 because it's starting from rest. V final would just be the square root of 2 times the acceleration times the distance. Let's put in some numerical values here. So this would be the square root of 2 times 150. So the square root of 600. And when we compute that, that's 24.5 meters per second. So notice 24.5 meters per second is less than 27.8 meters per second. So the runway, in other words, we weren't able to accelerate for long enough to take off. Insufficient. So, but you could think of this in other ways. So perhaps another way we could think about this would be, well, we know how fast we want to go. We could solve this expression for the distance that we need. So let's do that. If we solve this for d, we would have to divide by a factor of 2a. We can put these values in here. So this will be 27.8 squared over 2 times 2. We put this in, we get 193 meters. So notice 193 is greater than 150. Insufficient. Too short. Okay. That's just a simple example to get you started. Many problems are going to involve free fall. So let's look at some examples with this. And actually, your first lab exercise is free fall as well. So, and it will be central to projectile motion. So it's a really important topic in kinematics, and it's critical to know it inside and out as you're working on PH2011. It also happens to be probably the most common example of a constant acceleration. So does anybody know what the acceleration due to gravity at the surface of the Earth is? We give it its own letter, lowercase g. This is the acceleration due to gravity, basically at the surface of the Earth. And this is a little bit of a lie, or I should say, when we say that this is constant, if you look at small changes in height near the surface of the Earth, it's going to be constant. But if you were to drop something from very far away, the acceleration would change. And we'll get into that when we talk about Newton's theory of gravity in chapter 6. But for our purposes with kinematics, we assume that this is constant. And this is a number that you're probably going to have burned into your brain more than any other number in PH2011. So let's consider an example. So the example that I want you to consider is dropping an object from the observation deck of the Sears Tower. So, and let me give you a couple pieces of information. So we want to find two things. How long to hit the ground, and we also want to know the speed at the at impact. And I have to give you some information here. So the Sears Tower is 103 floors. Well, the observation deck is on the 103rd floor. And that is 412.4 meters from the ground. So let's try and draw a little bit of a cartoon here. You know, the Sears Tower, it's got like some, I don't know exactly here. You know, and so let's suppose this is the height that we're interested in, and that's 412.4 meters. Okay. So what do we know? We know this initial height. We know we're going to drop an object. So that means that our velocity, initial velocity, is going to be 0. We also know that we're talking about free fall. So in this case, the acceleration is going to be g, 9.8 meters per second. Something else we also need to be mindful of is a coordinate system here. So I would suggest, as you work through problems, giving yourself a little coordinate system to help keep track of directions. So a lot of times if you're talking about dropping an object, it's convenient to put the coordinate system at the ground. So what this means is that the initial height will be a positive number, but the acceleration is pointing down. It will be negative. Okay, so let's make use of our expression y is y naught plus v naught t plus 1/2 at squared. So we know that the initial velocity is going to be 0 because it's being dropped. We know that the actual final velocity or final height is also going to be 0 because it's going to land at y equals 0 if we put our coordinate system on the ground. And this acceleration is going to be g, and it's going to be negative because it's pointing down. So let's put that information in. Sorry, the t squared there. And so we can solve this then for t. So notice we would subtract, well here, I'll do it in 2 steps. So negative 1/2 gt squared is going to equal negative y naught. Those negative signs are going to cancel. We'd have that t is 2 y naught over g, and then we could take a square root of that situation. And let's put in our numbers. 2 times 412.4 times 9.8. So 800 over 10, it's about 80. It's about the square root. So this is going to be approximately 9 seconds. So it takes about 9 seconds if you were to drop an object. Now, there's a caveat here. This is assuming there's no air resistance or any other thing that's interfering. So this is not necessarily very realistic depending on the kind of object that you were to drop, but it allows us an opportunity to practice with this kinematics expression, and in this case to calculate a time. So that was what we wanted to know for part A. The other thing that we want to know is, how fast is this going to be going when it hits the ground? So we can do this in a couple different ways. Like I mentioned before, there's multiple ways to do this. One way would be to use our expression that we already used, or that we talked about that doesn't involve time. So I'll put this as delta y. The distance that we've gone through is going to be the change in height. So again, we wouldn't have an initial velocity. Our change in height is going to be y minus y naught. We're going to have a square root here of 2. Remember, the acceleration is negative 9.8. Now this delta y is going to be y minus y naught, but the final y, recall, is going to be 0 minus y naught was our 412. So part of why I'm being kind of careful with these signs is, notice we have a square root here. If we were being sloppy and we ended up with a negative number, it wouldn't make sense. We would get an imaginary result. So we have to be careful and make sure that our negative signs track. And so this would give us, when we crunch the numbers, this is 90 meters per second. So this is a little bit difficult to interpret. Let's convert our units to something more familiar. So remember our unit conversion, 3.1 miles in 5,000 meters. We know there's 3,600 seconds in 1 hour. So we can convert this from meters per second to miles per hour. You crunch this through, you find that this is 200 miles per hour. Yikes. But I told you, there's multiple ways to solve this. We could also just simply make use of the time that we already calculated, right? So the velocity, remember our first expression? V equals V naught plus AT. Well, we drop it. This would be 0. We know what the acceleration is. And we know what the time is. Get our 90 meters per second. And one other thing I would mention is I'm being a little fast and loose with the directions. So this velocity is a vector. This expression where we took the square root, really what we did there is we found the speed. If we wanted to be more diligent, we should indicate the direction that these are going. So the negative y direction, recall that the unit vector in that direction would be j hat. And since it's going negative, it would be negative j hat. So why don't we say this? This is the speed, but in vector terms, this would be negative 90 meters per second j hat. Just to be a little more careful. And let's look at one other example. So this was pretty simple because we just dropped an object. So the other example that I want you to think about is, suppose your object does have an initial velocity. So imagine, here's the situation that I want you to consider. Let me give myself a little more room here. Juggling. So think about juggling. And I want you to consider a ball thrown up at 15 meters per second. And we want to know how high does it go? And we want to know how long is it in the air? Okay. And like we did before, let's give ourselves a little picture. So we've got a guy juggling. The ball goes up. Now, I'm going to do something. I told you just now that it's convenient to put the coordinate system on the ground. Well, if your ball never gets to the ground, it's more convenient in this situation to put the coordinate system, the y equals 0 of your coordinate system, at the initial position and final position of the ball, or final height. So let's look at how high it goes. So we can get this. Notice we don't have any time information, so we can make use of our v final expression. Now in this case, what do you know about at the top? So at the top, the ball has to change direction. And so what that means is that there is an instant where it stops and turns around. So up here somewhere at the very top, the velocity is going to go to 0. So we can then solve this expression. We know the acceleration. We know the initial velocity. And we can find the height. So, and we can be, well, let's just solve this for the, let's call it height in this case. So negative. Notice the acceleration is g. That's negative as well. So this, when we divide this negative by negative, we'll get a positive number. So we can go ahead and let's put our numbers in here. This was 15 squared over 2 times 9.8. This works out to 11.5 meters. Okay. So we know how high it goes. And then for part B, how long is it in the air? Well, there's different ways we could go about this. We could use our y equals y naught plus v naught t plus 1/2 at squared. Now notice in this case, the initial height and the final height, because I put the y equals 0, the coordinate system at that plane, those are both going to be 0. And notice this has actually two solutions. Actually, let me put in g here. One solution would be to say t equals 0 would work. Alternatively, we can divide out one factor of t and then solve this thing for t. And I should say t equals 0, well, that corresponds to the time right before, right when they throw the ball, the juggler. So before it's left at t equals 0, that would be one time at which it's there. And then the other, if we solve this for t, what do we get? We would get negative v naught divide by g. There's a factor of 2 here as well. And if we put these numbers in, why does that keep popping up? This would be, so g is negative as well, so we'll get a positive number. The time always has to be positive. Or I shouldn't say not always, but time is generally positive. This initial velocity was 15 and gravity 9.8. So you can see this is going to be about seconds. So another way, so that's one way. Another way that you could go about this is to just say, okay, well, how long is it going to take to get to the top? And use our simpler expression where we know the initial velocity, and we know, like I mentioned, the velocity at the top is going to go to 0. So if you solve this for time, notice you just get time is v naught over a. Well, v naught over g here. Which is just the time to the top. It'll take the same amount of the time to come from the top back down to the bottom. So really, we would have to multiply this by 2. And then we would have the same thing as we have here. So just another way of thinking about that problem. But there's a couple examples. We looked at free fall, dropping an object off a building, and then also this juggling example. You have an object that has initial velocity. Where these problems get more complicated is if you have when the initial velocity and either y or y naught is not 0. In that case, you'll have something that has t squared and constant terms, and then it will become a quadratic. So we can talk about that, and you will see that in your homework. We'll talk about this especially with regards to projectile motion. So hopefully these examples help get you started with one-dimensional motion, talking about situations with constant acceleration and especially free fall, kind of the most common case of a constant acceleration that we encounter.